looking at acid-base titration curves, also known as pH curves, and indicator selection. So our goal is to draw and interpret curves for acids and bases, including equivalence points, endpoints, and then this would include indicators as well, choosing the correct indicator. So in a titration setup, if a student was to measure the pH, where would they do so to see a change? And what would happen to the measured pH if an acid is titrated with a base? So to see a change in pH in our acid-base titration setup, the pH is constant within our titrant here in our burette. Therefore, if we want to see the pH change, we need to be looking at the sample. So it would start with the pH of the sample, and then as I add titrant, the pH will increase or decrease depending on whether it's an acid and a base or a base and an acid. So what would happen to the measured pH if an acid is titrated with a base? So that means that an acid is present in the sample and a base is here. So the pH will start low because it's acidic. As I add titrant, it will become higher because we're adding a base. Now we typically stop a titration when it is neutral or has reached its endpoint or equivalence point. However, in a pH curve or a titration curve, we are measuring the pH of our sample here from 0 mils to an empty burette, so to 50 mils. So we're going to empty the whole thing. So we're going to go past that equivalence point because we are plotting it. So we don't want to stop there. We end when there's no more titrant left, typically. Okay, so to select the correct titrant to be used in the reaction, we need to determine if the sample is an acid or a base. If it's an acid, whether it's strong or weak, it doesn't matter. The titrant needs to be a strong base, okay? So NaOH, KOH, any strong base in solution. If the sample is a base, again, whether it's strong or weak, the titrant should be a strong monoprotic acid. Okay, the reason is, remember H2SO4, for instance, loses one H first and then a second H. So we don't want this reaction to be occurring at the exact same time as our neutralization reaction. So we use any of our strong acids except for H2SO4. Again, the word neutralize has a more general meaning than bringing the pH of a sample to 7. If it is when the substance is completely or partially lessening the acidic or basic properties of another substance. We saw an example where HCl and Na2CO3 react, where you're going to get H2CO3 and NaCl. Now, we started with a strong acid and a weak base, CO3 2-, and we create a weak acid and something that's neutral. So we have lessened the acidic properties, moving from a strong to a weak acid, and we've lessened the basic properties of our compound as well. So this is still considered a neutralization, even though it doesn't make water or completely neutral products. Again, it's something explored in great detail in Chem 30. A pH curve is a graph showing the continuous change of pH during an acid-base reaction. So let's draw the pH curve for the titration of HCl with NaOH. So what this is, remember, the pH is measured in our sample here. So the titration of HCl with NaOH is there, meaning that we are going to start with a low pH because we're measuring just an acid, and we're going to end with a high pH. Okay, so pH is plotted along the y-axis, and volume of titrant added is plotted along here. So that would be in milliliters. And if we know what our titrant is, we would include that information here. So in this case, because we're titrating with NaOH, we would include that in our title. All right, now typically what we think is that a pH curve should be kind of linear like that. Unfortunately, it's quite interesting. It's very different. The pH is fairly constant as I start to add some titrant. The reason is there's so much acid here in comparison to the few drops that we've added of NaOH that the pH doesn't change very much. Remember, pH is a power of 10 of the concentration. So the pH, for it to change by a power, to go up by 1, the concentration has to increase 10 times. Okay, so what actually happens is we get like this big swoop. All right, now it's not typically as perfect as this. Sometimes it can be kind of elongated, but we get this step basically, okay? So from our low pH to our high pH. And I know that there's only one equivalence point, and we'll talk about that a little bit later, but an equivalence point is where in the middle of our high and low. Okay, so it's the midpoint. This is called the equivalence point. And it's when the number of moles of acid is exactly equal to the number of moles of base. Meaning we've added the perfect amount of titrant here, that we've neutralized all of our HCl, but we have not added more NaOH than necessary. So there's no limiting in excess. We've used up both. All right, a few other little labels. This was the initial pH of the sample. That's where the pH curve is going to begin here. And this is going to be the approximate pH of the titrant. And I say approximate because some of it has actually been used to neutralize our HCl. So it's not a perfect sense of its pH, but it's pretty close. All right, now when we stop our titration, we want to stop our titration at the equivalence point. And so hopefully that this value of volume of NaOH added would match our titration data. I mean, fingers crossed. Hopefully we're really good at it. Now note that if I stopped my titration here, the difference in the volume of NaOH added is very small. Same with if I stopped my titration up here. So what this is important for is the fact that we could stop our titration anywhere along this like straight up and down curve and not influence our results very much. Therefore, within this bracket is where we want our indicator to stop, to change. So choose indicator to change color in this region. And remember, a change in color represents our endpoint. So our endpoint can be anywhere in this area. And again, it's okay because the amount of titrant added here versus the amount of titrant added here, the difference is so slight that we really won't see it, maybe one drop. Okay, I don't want my indicator to change up here because that's quite a significant difference. Same, I don't want my indicator to change too soon. So making sure it's right along that step is important. All right, I think that covers everything. Okay, so the initial pH of the curve must be the pH of the sample. We noted that. The equivalence point is located at the midpoint of the steepest drop or incline of the plotted line. After excess titrant, whether that's acid or base, has been added, the pH is near that of the titrant. So that was at the end, this portion. The number of equivalence points must match the number of quantitative reactions happening in the reaction. Okay, so for instance, if we have a monoprotic sample, it will have one equivalence point. So something like HCl was monoprotic, so it had one equivalence point. Something like H3PO4 is a sample. Remember, I'd still be titrating it with NaOH. It has 3 H's, or 3 qualitative reactions. Therefore, it's going to have 3 equivalence points. So it has 3 steps is what that's saying. 1, 2, 3. Those are the equivalence points. And I want to stop titrating at the end when I have reduced all of the acidic H's. Okay. Okay, so choosing an acid-base indicator. Well, what is it? It's a substance that changes color when the acidity of a solution changes. An indicator tells the chemist when to stop the titration, aka the end point. Therefore, to be effective, it must also change color around the equivalence point. We talked about this. We want our titration indicator to change somewhere along this steep section. I don't want to change it too soon because that is not anywhere near my equivalence point. Now I can have a range that's slightly high or slightly low, again, because the difference in volume is so slight. So draw the pH curve for the titration of 10 ml samples of 0.1 moles per liter sodium hydroxide solution using 25 ml of 0.04 moles per liter hydrochloric acid. Include pertinent pH values, the equivalence point, an indicator that would be appropriate, and the color change of the indicator throughout the titration. Whew, okay. I'm just going to make this small so our pH curve can be nice and large. So, draw my axes here. So we're going to label this as the pH. And now, just looking at this, it says samples of sodium hydroxide using hydrochloric acid. So if we were to draw our titration, HCl is in my burette and NaOH is in my sample. So I'm starting with a high pH. And because NaOH is monoprotic, it's only going to have 1 equivalence point. So start high, 1 step. Now, we have some other labels to include. Oh, sorry, I should have added volume of HCl because it's our titrant added, and our burettes measure in milliliters, so that's what that unit would be. Okay, so our pH up here is the pH of the sample. So we can find the pH of the sample. We have NaOH, which is composed of an Na plus and an OH minus ion. Therefore, if we have the concentration of NaOH, the concentration of OH will be the same because of our 1-to-1 ratio. I could show that, and I probably should, but the concentration of NaOH is 0.1. Therefore, the concentration of OH ions in solution is also 0.1. So we can find the POH, which is the negative log of the OH minus concentration. So negative log of 0.100. And we get a POH of 1. It should have 3 decimals. We are plotting pH, not POH. So pH is 14 minus POH. So 14 minus 1.000 is 13.000. And that is the pH to begin with here. Now, we could also find the pH of our titrant. So at the end here, it's approximate. Again, it's not a perfect number. It may be slightly higher, but that's okay. Okay, so HCl reacts with water to make H3O and Cl minus. The concentration of HCl is equal to the concentration of H3O because they have a 1-to-1 ratio. So our concentration is 0.04000 moles per liter. Sorry, too many zeros there. The pH is the negative log, the concentration of H3O, and that's the negative log of 0.0400 moles per liter. So we get a pH of 1.398. Okay, now it's not really the best idea to say that the midpoint is the average of these two. It's close, but it's always the average of when we start the downward and start the upward. And because this is usually pretty long and drawn out, it's not perfect. Okay, so our equivalence point is somewhere in the middle here. And because HCl and NaOH make water and NaCl, which is neutral, I would expect our equivalence point to be out at approximately 7. Okay, the last value we could add here, hopefully we've stopped titrating at our equivalence point, and the volume of titrant required to get there was 25 mils. Okay, so that value should be at approximately our equivalence point. Pick an indicator that would work. There's a ton of different indicators that would work for this graph and change color somewhere in and around our steep point here. I chose chlorophenol red. So note the color change of the indicator throughout the titration. So what would the indicator start with? Well, it says that the indicator changes from yellow to red, meaning that it's red when it's basic. So it's going to start red. Hopefully, around our equivalence point here, it's going to turn orange. Oopsie. And as we move past our equivalence point into a lower pH, it will become yellow. So our indicator in the pH curve will transition from red to orange to yellow. If we were to just do a titration, not a pH curve for this, we would stop when the indicator changes from red to orange. All right. All right, so we are going to draw and completely label the pH curve for the titration of phosphoric acid with sodium hydroxide. Include the reaction at each equivalence point. Okay, so I've already kind of noted this because H3PO4 reacts with NaOH to make 3 waters and Na3PO4. There's 3 H's, meaning that it is triprotic, and it will have 3 steps or equivalence points. So, we weren't given any values, so we don't need to include any pertinent values here. And then this would be the volume of NaOH added, and that's in milliliters. Okay. We're starting with our acid because phosphoric acid is titrated with sodium hydroxide. Therefore, phosphoric acid is our sample. So we're going to have 3 steps. 1, 2, 3. They don't all have to be the same height. They can be different heights of steps. It's not building code here. Okay, and we know that there are 3 equivalence points. All right, so write the reaction at each point. So at the first point, we have H3PO4, and it's going to react with 1 mole of NaOH because the first reaction is just the removal of 1 H. Okay, now I'm going to simplify just a little bit here because I know the Na isn't really making a big difference. I'm going to just include the OH minus because it's the base. We know that Na is a bit of a spectator if we were to draw or write, net ionic equation here. Okay, H3PO4, which is aqueous, forget my states here. We're going to make 1 water and an H2PO4 minus. Now that H2PO4 minus is what's going to start to react here when we add another mole of OH. So we've continued to add OH minus here, or NaOH. More volume has been added. Okay, so we make another water, and we're left with HPO4 2 minus. These are aqueous. Okay, last step. The only thing remaining in my sample that's acidic is HPO4 2 minus. So it reacts with 1 more OH minus. So we've added, again, 3 times as much OH. And we're going to be left with water and PO4 3 minus. It cannot continue to react because there's no more acid molecules. So This will be our end point. End point, because acid is completely neutralized. Okay, so each equivalence point represents the point where another H is lost by the acid. Okay, so we're just going to show the removal of one H, each time. Alternatively, if we were titrating a polyprotic base here, it could represent another H being gained if we had that polyprotic base. Our final example here shows the titration of 10 ml samples of oxalic acid using standardized potassium hydroxide. One thing to note, they use this big M, so volume of 0.100 moles per liter NaOH added. Okay, so that's in milliliters. Big M is equal to moles per liter. Chemists are just lazy, and that was a big unit to write, so they continue to just shorthand it. Okay, so we're determining the concentration of the oxalic acid solution using this pH curve. So remember, we want to choose our last equivalence point as our end point. Okay, so we can read the volume of titrant required. So the volume of NaOH required was 20 milliliters in this case. And we were given 10 ml samples of oxalic acid, and we have the concentration of NaOH in the graph here. So we're going to write a balanced chemical equation. Oxalic acid has two H's, and we write them at the beginning and the end of the formula, which is a little bit weird. We're going to need two KOH's to neutralize that to make two waters, and K2OOCCOO, which is aqueous. I know it's weird. I said the H's have to go on the beginning and the end of oxalic acid, but we write metals first in an ionic compound, so K2 gets written together. Writing out what we know, we have the volume, and we're looking for the concentration of oxalic acid. We have the volume of our NaOH, again, read from our graph. It was our 20 mils, and the concentration was 0.100 moles per liter. Okay, just using some unit analysis, 0.0200 liters of oxalic acid times its concentration. Or sorry, that was KOH, my mistake. Liters cancel, we're left with moles of KOH. We need to cancel moles of KOH. They go on the bottom of our mole ratio, and moles of oxalic acid are on the top. So that's a 1/2 ratio. Moles of KOH cancel. Now we want our units to be moles per liter, so I'm not going to cancel moles. I'm simply going to divide by liters here. I'll show another 0, and I get 0.100 moles per liter for oxalic acid. If you were to pick an indicator for this titration, what could we use? Well, we want to have our end point at the second point here. So something to change around 10. I think that phenolphthalein would be a good choice in this case because it changes color around our second end point. We don't care about the first one.